So I'm going to start with talking about the science of climate change. This is not something that will be examined because this is an economics course and it's not a course in atmospheric chemistry or atmospheric physics. However, in order to understand a problem and understand solutions to a problem, you need to roughly understand the problem itself, right? So that's why I start here. Some of this material you may have seen on the telly or you may have read about it in the newspaper. There's a lot of material about climate science out there. A lot of it is fairly confused. Some of it is outright wrong. So I'm just going to tell you my version of this story so that we're all roughly on the same page and all have the same understanding of what is going on. I'm going to start at the beginning. So what you're looking at is no less than 9 pictures, and they're all observations. So here on the for you extreme left, we are looking at the atmospheric concentrations of the 3 most important anthropogenic greenhouse gases. That's carbon dioxide, CO2, that's methane, CH4, also known as natural gas, and that's nitrous oxide, N2O, also known as laughing gas. And what you see, and this is the bigger pictures, are over a period of about 200 years. No, sorry. The bigger pictures are over a period of about 10,000 years. So since the start of the agricultural revolution, we see a more or less stable concentration of these greenhouse gases in the atmosphere. And then towards the end, and that is a smaller inset, that's the last 200 years or so, we see a steady increase in the concentrations of these gases. And this is the start of the Industrial Revolution, right? So this is sort of when human civilization started, but towards the very end, these things jump. These are observations. You may wonder where does this come from, right? Because nowadays we have modern chemistry and therefore we can measure the contents of the atmosphere. How did people do this 10,000 years ago? Well, obviously they didn't know much chemistry then. If snow falls on an ice cap, snow is fluffy, so it has actually a lot of air around it. So you have a snowflake falling with a lot of air around it, and other snowflakes fall on top, and some air, and then it gets sort of frozen and condensed and everything, compacted. And some air then gets trapped in the ice, and then more ice accumulating on top and more ice accumulating on top. And essentially what you have is that if you drill down in an ice cap, you essentially, the air that you find travels back in time. What people have done is drilled ice cores and analyzed the composition of the air that they found in trapped in the ice, and that is where these measurements come from, in different colors, different sites and different sampling schemes and what have you, right? Different ways of it. But they all agree, roughly constant concentrations, and then a sharp jump. These are also observations. I'll come back to the greenhouse effect in a minute. What we've seen over the last 150 years or so is that the global mean surface air temperature has gone up by about 0.7, 0.8 of a degree Celsius. If the air gets warmer, then water gets warmer as well. If water gets warmer, it expands. And we've also seen sea level go up over the last century or so. And what you would expect is if it gets warmer, you would have less snow. And we've also seen, at least in the northern hemisphere, the extent of the snow cover go down. And all these observations are consistent. Why do we worry about these greenhouse gases? Why are they called greenhouse gases? Not really because they are a greenhouse, but this is just the way Fourier back in 1827 described this effect. Even though it's a very different effect what you would see in a normal greenhouse, but it's known as the greenhouse effect. Works something as follows. The sun is somewhere out there, sends out a lot of energy in all directions, small fraction of it in our direction, and that energy from the sun hits our planet. Some of it hits the top of the atmosphere, is reflected back. Some of it is reflected back at some point in the atmosphere, at clouds or particles that are there. Some of it is reflected back at the surface of the planet. And another part of that energy is absorbed by the planet. Now that cannot be the end of the story, right? Because if the planet Earth would absorb more energy and more energy and more energy, then it would get hotter and hotter and hotter and hotter, and it would have melted and evaporated a long, long time ago. Right, so that cannot be the end of the story. It's also pretty clear that it's dark at night, right? So the Earth does not emit visible light, right? Otherwise the ground would light up. It doesn't. But the Earth emits energy in the infrared part of the spectrum. And that is what you see going on here. The planet has to be in some sort of energy balance. The energy that comes in has to come out as well, otherwise it will just keep getting warmer and warmer and warmer. That infrared radiation, some of it is reflected back in the atmosphere, goes back to the planet, but most of it gets out. Why does it do this sort of stuff? That's where greenhouse gases get into the picture. By definition, greenhouse gases are transparent to visible light, but they're opaque to infrared light. So if a ray of solar energy hits a CO2 molecule, it just passes right through as if it isn't there. If a ray of infrared energy hits a CO2 molecule, it is absorbed. It just absorbs the energy, gets into an excited state. Again, we have to obey the laws of conservation and that sort of stuff. That a CO2 molecule cannot keep that energy forever. So it gets hit by a ray of energy, it goes into an excited state, and a little bit later it goes back into its normal state again and re-emits the energy that it has just absorbed. But it re-emits that energy in a random direction. Whereas the infrared radiation is all from the Earth is all going this way. When it gets hit by a CO2 molecule, it can be re-emitted in any direction. It can be sent to outer space, it can be sent to other parts of the atmosphere, or it can be sent back to Earth. So what does that mean? That with greenhouse gases present in the atmosphere, there is sort of a barrier for energy to leave the planet. So in equilibrium, in balance, there's more greenhouse gases in the atmosphere, more energy would be stored in the planet. Of course, we still have to be in a long-term equilibrium, but with more CO2 and other greenhouse gases in the atmosphere, that equilibrium will be at a more energetic state, a state in higher temperatures. Without the atmosphere, the Earth would not be 15 degrees Celsius, but would rather be minus 15, perhaps minus 20 degrees Celsius. So it would be roughly 33 degrees colder without the atmosphere, without greenhouse gases in the atmosphere, than what it really is. You could probably agree that a natural greenhouse effect is a rather good thing, because minus 15 as an average is rather chilly, right? So now if you put press here. If you put more CO2 in the atmosphere, you would expect the temperatures to go up, and that is exactly what we saw, what we have seen, right? I'll come back to that. CO2 is not the only thing that we're doing to the atmosphere, not the only thing that we're doing to the climate. This is the radiative balance. So this is essentially the change in net energy, or around radiative forcing, since pre-industrial times, different between now and pre-industrial times or recent past. And CO2 is one of the biggest ones that you see there, but it's definitely not the only greenhouse gas. There's methane and nitrous. As I said, there's also the halocarbons. There are other greenhouse gases. These are things we emit. Ozone is also a greenhouse gas. We don't emit ozone, but stuff that we emit makes ozone at lower levels or destroys ozone at higher up in the atmosphere. So that affects the radiative balance of the atmosphere. We change constantly the surface of the planet. We cut down trees. If you look at trees from a satellite, they're dark. They absorb a lot of energy. If you replace trees with grass, grass is much lighter, so it reflects more energy. So that affects the climate as well. And we are emitting all sorts of soot and that sort of stuff that lands on snow, and therefore snow becomes less white, becomes more gray, and that also changes its reflective properties, known as albedo. We put all sorts of particles in the atmosphere by the combustion of coal and wood and what have you. Also changes radiative balance directly, typically a cooling effect, but it also changes cloud formation. And clouds also have an impact on climate. A very confusing one, right? I mean, on a winter's night when it's a clear sky, it gets horribly cold. But on a summer's day, when there's clouds, it gets, oh damn, it gets colder as well. When it's a clear sky in winter, it gets cold, right? When it's a clear sky in summer, it gets hot. So it did get it right. So depending on when the clouds are, by day or by night, in winter or summer, also in fact, depending on whether the clouds are low or high in the atmosphere, they have a different effect on the temperature. But people reckon that because of the additional clouds due to additional particles in the atmosphere, the additional clouds in the atmosphere, that's a net cooling effect, although the uncertainty about this is rather large. And then, of course, there's also other things that have nothing to do with human intervention. Also, the sun sort of sometimes sends more energy towards us, sometimes sends less, sometimes we're a bit closer to the sun, sometimes we're a bit further away. People reckon that had a small positive effect or a small warming effect in the climate. So the story is much, much wider than just carbon dioxide. There's many more complex things going on. CO2 is also not at all a simple story. What you're looking at here is a schematic of carbon cycle. The black numbers are pre-industrial. The red numbers are changes since pre-industrial. The blocks are stocks. The arrows are flows of CO2. And what you see, right, we're now in winter. There's no leaves on the trees. Leaves are made of carbon, and they've all rotted away, and all that carbon is released, made of carbohydrate. All that carbon is released into the atmosphere. So that's this arrow here. But then, when spring comes and all the leaves grow back, a lot of CO2 is sucked out of the atmosphere, and that is this arrow here. So the vegetation constantly exhales and takes in CO2, just like we do. And over the seasons, and because most of the terrestrial vegetation is in the northern hemisphere, because that's where most of the land is, that actually has a net effect or a differential effect between the seasons. And those flows are about 120 gigatons of carbon every year. The ocean does something similar for very similar reasons. So it takes up CO2 and it pumps it out again to the tune of about 70 gigatons of carbon. And then what happens here is us taking old plant material and burning it, sending it to the atmosphere. When this cartoon was drawn, that was about 6 gigatons of carbon per year. It's now about 8 or 9. And this confuses some people, because human emissions are 6 per year. Natural emissions are about 190 per year. So how on earth can this have an effect on the climate, right? The reason is very simple. These 200 or 190 that are emitted every year are a little bit later in the year or early in the next year taken up again. Whereas the 6 or 8 or 9 that we're pumping into the atmosphere, there is no natural counterbalance there. So this is a net addition to the stock of CO2 in the atmosphere, which has gone up from about 600 gigatons to about 750 since the start of the industrial revolution. Yes, one reason why this cartoon is up here. The other reason is that the climate system is a bit more complicated, right? Because one of the major carbon pumps is terrestrial vegetation. If it gets warmer, if you travel, say, from the Netherlands to Spain, or from Maine to Florida, you would see that as you get into warmer climates, vegetation changes. So if, because of this, it gets warmer in the atmosphere, it also means that the vegetation would respond to that, different plants would grow, and therefore these fluxes will also be affected by climate. These are not driven by the seasons only, they're also driven by rainfall, they're driven by temperature, and so on and so forth. So the climate has an immediate effect on how much CO2 there is in the atmosphere, right? So that's an additional complication that just makes life confusing for people who want to study, or makes it interesting, right, for people who want to study climate science. But yeah, all these complications aside, what we've seen is the concentration of greenhouse gases going up. From first principles, we would expect that therefore the planet would get warmer, and that is also what we have observed. There's a lot more going on. If it gets warmer, then the air can contain more water vapor. Water vapor is also a greenhouse gas, and that would further increase the warming. And then, of course, we would see ice melting, snow melting. That would make the surface of the planet darker. That would also further increase warming. Vegetation may change. That would affect warming, and so on and so forth. Cloud cover would change. That would affect climate change further, right? So there's a lot of things going on. So what people have done is, I mean, based on first principles, you can say we have more greenhouse gases in the atmosphere, then we would expect it to be warmer. And you have to come up with a pretty crazy mathematical model to sort of have that sort of the first order effect is in this direction, that all the feedbacks sort of push you back to the original position. That would be a bizarre model, but actually we know the primary feedback effects, and they probably strengthen the initial warming. But based on first principles, we cannot figure out by how much. First principles, by the way, was sorted out by John Tyndall in the middle of the 19th century. And the first predictions of global warming due to CO2 were at the end of the 19th century by Santa Arrhenius. So what people have done, rather than reason from first principles, they've tried to put all these mechanisms that I described and a good few more in what are probably the most complex numerical models around, the so-called general circulation models. And what you're looking at here are the results, or some results of these models. And let me take you through this graph. So in black, we're looking at the smoothed observations of temperature. This one you've seen before, global mean. Here it's split out between land and ocean, and here it's split out between the 6 inhabited continents. So these are observations. In pink, we're looking at what did the model say would happen during the century if we include all known forcings of the climate. It's not quite a prediction, because these predictions were made in the year 2000 about what would have happened in the previous century. It would have been much stronger had they done this in 1900 and come up with this prediction. But of course, we haven't any computers then, right? So we could not have done it. But if we include everything that we think affects climate, then the models, and there's a lot of uncertainty about the models, and there's a lot of differences between models, then the models predict the pink range. What you see is that the observations are somewhere in the middle. This gives you some confidence that these models are not complete crap, right? If we do the same exercise, but now we assume that additional greenhouse gases in the atmosphere do not matter, and we run the same models under otherwise the same conditions, we get the blue ranges. And what you see is that the blue and the pink separate towards the end of the 20th century, not much before. What you also see is that the observations get out of the natural forcing, outside of the range of natural forcing. Now, these ranges are not a range of the true uncertainty, and they're not confidence interval in the statistical sense of the word. Rather, they're a range of model outcomes, and all the models try to do their best. So this is a range of means rather than a confidence interval. But still, what you see is that if you believe that greenhouse gases have an impact on climate, then what we have observed over the 20th century is roughly as you would expect. Whereas if you don't believe that greenhouse gases had an effect on climate, then what we have observed over the last century is very, very odd. And this suggests that indeed greenhouse gases have had a role to play in the observed warming, and sort of gives us some confidence in these models and allows us to use these models in the future. So here again, same picture. And these are the observed temperatures over the 20th century. And then if we run the same models forward, these are the projected temperatures in the 21st century. And yeah, chances are that at least one of you will make it to test whether these predictions are true. Right? I won't be there, but one of you might well. There's a lot of uncertainty about the future, right? And the sort of shaded areas that you see here is uncertainty about how the climate would respond to a certain impulse of greenhouse gases. There's a lot of uncertainty about that, as I described. But of course, we also don't quite know how much we will be emitting over this century, right? future is fairly uncertain. Future emissions depend on future economic growth, future population growth, future energy use, and so on and so forth. All these things are fairly uncertain, and that uncertainty is represented by the different colored lines. And if you combine those two uncertainties, then what we find is that by the end of the century, it may be 1 degree warmer than it is today, maybe 4 degrees warmer, or even 6 degrees warmer than it is today. In 4 weeks' time, maybe 5, I will ask the question, so what? Right? I'm going to pause that or stall that for now. And we're going to come back to the question, why do we actually need to worry about this months later? We've shown so far essentially pictures of total or global average warming. The pattern is not at all homogeneous across the planet. So this is the projected warming in the near future. This is the projected warming towards the end of the century. And you see here 2 clear patterns. One is that the land warms faster than sea. That follows basically from the greater heat capacity of water relative to soil. And that, of course, matters to humans because most of us live on land rather than out in the ocean, right? And you also see a distinct geographical pattern, and that is that the poles warm much faster than the tropics. There are darker colors there. We can also see in these models, pictures not shown here, that nights tend to warm faster than days, and winters tend to warm faster than summers. There's much more to climate than just temperature. There's rainfall as well. What you're looking at here are projected patterns of rainfall changes. They call it precipitation to also include snow and other forms of water, also falling in different forms. In December, January, February, our winter, and in July, August, our summer, according to one particular scenario. Of course, you can repeat this for all sorts of different scenarios. There's a lot of information on this graph. The colors are the average of multiple models. Blue means it's getting wetter. Brown means it's getting drier. Shaded areas mean shaded areas means that 2/3 of the models agree on the sign. Areas that are not shaded means that the models can't quite figure out what the sign of the change is. Right? You see that the shaded areas are actually in the minority, right? There's a lot of uncertainty about what climate change would do to rainfall patterns. Some things are relatively clear. One thing that most models agree on is if it gets warmer, water is pushed from the tropics and rainfall is pushed from the tropics and subtropics towards the poles. So you see it drying in the mid-latitudes, you see it wettening in the high latitudes. First side, that is fine on the northern hemisphere. In the southern hemisphere, that's rather unfortunate, because the closer you get to the poles, the less land there is. And more of the water, or some of the water that used to fall over southern Africa and help people and plants and that sort of stuff, is now falling or is likely to fall over the Southern Ocean, where it's no good to anybody, right? It's not that it will be more or less rain, it just will fall in places that are not very helpful to humans, right? Again, a bit of confusion here. If we focus on where we are, then what you see is is that in winter, England is projected to get wetter, and in summer, England is projected to get drier. So if you hear somebody on the telly or so say, because of climate change, we will have more droughts and more floods, that is not because they're complete idiots, but it is because they're talking about different seasons. Floods are concentrated in winter. You will see an increase, or we're likely to see an increase in rainfall in winter, so that will bring more floods. Droughts are concentrated in summer, definitely in southern England. We expect longer spells of drought in summer. And that's perfectly consistent with saying there's also going to be more floods in winter, right? But yeah, as I said, these things are rather uncertain. Press here. Will not stop there. Sea level will rise. What we're looking at here are alternative models projecting sea level rise. Again, there's some confusion there. The main effect here is thermal expansion. As water warms, it expands. You may think I'm nuts. If you have a cup of tea, you let it cool down, it doesn't shrink. Well, actually it does. It just shrinks by a tiny little bit. You just can't see it with the naked eye. But it does shrink a little bit. Similarly, if sea level, if the waters in the sea warm up, they expand. Only a little bit. You may wonder, why is that a human problem? It's very simple. The ocean is on average 3 kilometers deep. So if the ocean expands by a tiny little bit, then on a human scale, say 2 meters, that is actually quite a bit, right? That is why expansion of water matters. Again, not a uniform pattern across the globe. That's what you see here. And there's of course also ice melting. If ice that is floating on water, as we see at the North Pole, melts, then that does not matter for sea level rise. As Archimedes sorted out 3,000 years ago, right? If ice that is on the land melts, it's ice on Greenland or ice on Antarctica, then it does raise sea level, right? Perhaps by quite a bit, probably not during this century. These are the various contributions to sea level rise of the current century, where thermal expansion is the most important one. On the longer term, if Greenland melts completely or slides into sea, that would raise sea level by about 7 meters. 7 meters. If West Antarctica melts, then that would raise sea levels by about 5 meters. That makes a total of 12, and we're sort of roughly at the top of the building here. If we were at sea level, which we're not, right? If East Antarctica melts as well, then we can add another 60, 70 meters of sea level. And then we are at the top of the building, including the top of the hill, right? Probably won't happen this century. May happen this millennium, right? At some point. Doesn't stop there either. If temperature patterns change, then pressure patterns will change. That means that winds will change. They might change direction. They may also change storm regimes. Tropical storms are the ones that strike people as particularly interesting because they are so violent. Terribly complex beasts. Nobody fully understands them, but the current received wisdom about what climate change will do to tropical storms is not that tropical storms would hit London or something. That will not happen. They will not expand their area. They will probably not expand their frequency either, but they will probably become more intense. They will become more violent, which is a concern. Ditto for extratropical storms, stuff that does hit London. They will probably become more intense as well. This matters for impacts, right? Because if this year you're hit by a violent storm, and then next year you're hit again, then you actually less than double the damage. Because a lot of the vulnerable stuff has been blown away in the first storm. So frequency, I mean, damages are less than proportional to the frequency of storms. But the power of the wind is the speed of the wind to the power 3. The force of the wind is the speed of the wind to the power 3. So if you have a slight increase in wind speed, you actually have a large increase in the force that wind exerts on buildings and trees and all that sort of stuff. So if storms become more intense, then we actually say 10% more intense, then we see the damages increase by 1.1 to the power 3, not by 1.1. So it's actually the intensity of storms that we should worry about rather than the frequency of storms. Rainfall I talked about. Final thing that I want to mention is ocean acidification. Some people get terribly upset by this term. The proper English name for CO2, hardly ever hear anymore, particularly when it's dissolved in water, is carbonic acid. That's the proper English word. Not so much worried about carbonic, but we are worried about the acid. It is a mild acid. If there's more CO2 in the atmosphere, then because of partial pressure, there also has to be more CO2 in the ocean. Otherwise, you would be in a chemical imbalance. If there's more CO2 in the ocean waters, then that means that the waters become more acidic or less alkaline, depending on who you believe. And that is bad for anything that is calciferous. So, you're cleaning your bathroom, and there's a lot of sort of in the bathroom. There's sort of these white stains that appear. What is that? That's calcium. That's calcium that's deposited by your shower or by your tap. The way to get rid of those stains is to pour acid on. That's all the cleaning materials that you would use to clean your bathroom or your kitchen. They all have some form of acid in them that takes away the calcium. Now, if you're a coral or you're a mollusk, then your skin, your outer hull, is made of calcium. So if you put these animals in an acidic solution, their skin dissolves, right? And anything with an exoskeleton that is hit by acid is in trouble. Now, it's not the case that the ocean will suddenly jump from being alkaline to being very acidic. There will be a small increase in acidity of the ocean, but it will change the balance of animals with animals with an exoskeleton versus animals that have an internal skeleton or no skeleton. And calciferous species, as they're known officially, will be relatively in trouble if ocean water becomes less alkaline. Okay, as I said, in 4 or 5 weeks' time, we'll return to what do these impacts all mean. This afternoon, I'm going to return to the question, where do these emissions come from? And then immediately, what can we do against those emissions? What are the technical options? So I see you guys at 3 o'clock, and I'll see you guys next door.